Hi, Mr. Vandergrift, come on. I've been averaging 15 miles an hour, every day through here, every day. So are you trying to tell me that this one time that I was hungry and I needed to get to Chick-fil-A and I drove 17 miles an hour? You're gonna bust me for that, even though I've been averaging 15 the whole time?
Yes, it wasn't just the average through there. It was actually the one point that I saw you.
So you're telling me that even though my average was 15 miles an hour, it was that rate at a particular point in time that was important, almost like a rate in one particular instance.
Yes, I am.
So maybe something like an instantaneous rate.
Correct.
Huh. Sometimes we need to know more than just the average reaction rate. It may be important for us to find out what the rate is at a certain point in time so that we can have a better understanding of that reaction. Take, for instance, this reaction, the decomposition of hydrogen peroxide to form water and oxygen gas. This rate doesn't stay the same over time. It will change, as you can see on this graph. Now this would be the reactants, the concentration of the reactant, in this case hydrogen peroxide, in molarity, moles per liter. And you can see that over the course of time you have less and less reactant, but it's not at a steady, uniform rate. The rate changes. So how do we determine at a certain point in time what the rate's going to be? We can do this by finding what we call the instantaneous rate. And here's how we can do it. Let's say I want to find the rate at a particular point. I'm going to do it at 4 seconds in. So this point right here. How can I determine what the rate is at that point right there, the instantaneous rate at 4 seconds? The way I can do it is I can make what's called a tangent line. I'll take a straight edge and I'll place it up against the line at that point. Notice I tried to make the distance, the angle between my straight edge and the rest of the curved line equal. I want equal amounts of space between. Once I do that, then I can draw my line, including the dot in question in the process. Now I can find the slope of that line by using a classic rise over run, and when I do, I will find the instantaneous rate. So if I find my change in y over my change in x, the classic way of finding the slope, I will do the same thing as finding the change in H2O2 over the change in time, my instantaneous rate. So once I have my tangent line, my straight tangent line, I can find the slope from that line, taking 2 points on the line, and then I'll have my instantaneous rate. So what I've done is I've found 2 points on my line, including the one in question. Now I'll find out what my coordinates are, x and y coordinates, right? So for this first one, I'll put my straight edge straight down, and I see that I'm about at 2.2 seconds, aren't I? So this one is 2.2 and right about 0.5. Yep, 0.5. So there's 1 point, and here's the other. Let's see. So I said it was going to be at 4 seconds, just double checking that. And for my y, I'm about 0.35. 0.35. Now I can determine my slope, and in doing so, determine my instantaneous rate. So when I plug in my numbers, I find that I have a difference in concentration of 0.15 moles per liter from one point to the next. And that's over the course of 1.8 seconds, the difference in my time amounts. 0.15 divided by 1.8 seconds gives me 8.3 times 10 to the negative 2 moles per liter second. That is my instantaneous rate. Notice that if I took the rate at a different point, say up here, that my rate would be remarkably different from this one right here. That's the reason why we pick a particular point and we use a tangent line to make sure we have the right slope. Thus, the right rate. So, to recap, we would be given these points along this line through experimentation. We would find out what kind of concentration we have at a certain period of time. And this curved line would be the result. Now we pick a point along that line where we want to find the instantaneous rate. We make our tangent line. We take 2 points on that line and we find our slope, instantaneous rate. You know though, there is another way of finding instantaneous rate. And that's through what we learned in the last section, rate law. Let's say we have this reaction right here. The reaction between nitrogen monoxide, also called nitric oxide, and hydrogen to produce dinitrogen monoxide and water. In the problem they tell you it's first order in hydrogen, second order in nitric oxide, and the rate constant is 2.9 times 10 to the second 1 over molarity squared seconds. What is the instantaneous rate when the concentration of nitric oxide is 0.002 molar and the concentration of hydrogen is 0.004 molar? So how do we do it? Let's take a look. Okay, so I've made a generic rate law for this reaction using my reactants in question. The first thing I do is I take note of the orders that they give me. They tell me that it's first order in hydrogen. What does that mean? Hydrogen to the first power. So second order in nitric oxide means that I put a 2 right there. So whatever concentration I get for nitric oxide, I'll have to square that. Then this is my rate constant, my K. So I'll go back and I'll fill these things in using the numbers that were given to me, and we can find the instantaneous rate. Okay, so now I've filled in my numbers that were given to me in the problem. My rate constant of 2.9 times 10 to the second, 1 over molar squared seconds. My concentration of nitric oxide at 0.002 squared, multiplied by my concentration of hydrogen gas, 0.004 molar. And by the way, probably important to use some parentheses here when you're doing this, just to keep things as error-free as possible. When I do that, my final is 4.64 times 10 to the negative 6 molarity per second, or moles per liter second. This is my instantaneous rate, using a rate law based on this reaction. You get it? Most chemical reactions actually occur in a series of steps. Not just one, but a few. Let's take, for example, this reaction. The reaction of nitric oxide, hydrogen gas, to give us nitrogen gas and water. You'll see that there are a series of steps that occur to make this happen. Each of these steps are known as elementary steps. So here's an elementary step, here's an elementary step, and here's an elementary step. When we add these steps together, we get our final reaction. You see? So by the time I cancel everything that's on the left and right that are the same, I get my reaction, the one that I wanted to begin with. Just to show you that these elementary steps do add up to the final reaction. Now again, we call this a complex reaction because it has more than just one step. If it has 2 or more steps, that's a complex reaction. Now we call the step-by-step process of this the reaction mechanism, how each step proceeds working towards this final overall reaction. Now you'll also notice we have some compounds in this series of steps that may be products in one step, but they are not products in the final reaction. They're products in one step, but then they're used as a reactant for another step, like N2O2. When you have a substance that's produced in one step, but consumed in another, we call that an intermediate. Intermediates do not survive the full reaction. They are not found as products at the end of the reaction. They are consumed at some point in subsequent steps in that reaction. So once again, a complex reaction is a reaction that occurs in two or more steps, and those steps are known as elementary steps. When you combine the elementary steps, you get the reaction mechanism. And if you have a compound that's produced in one step but consumed in another, we call that an intermediate. Can you see another intermediate in this reaction sequence? Sure, dinitrogen monoxide is an intermediate, isn't it? It's produced here in this step but then consumed in the next step, and it is not a product in the final reaction. Now, do you have someone in your family that tends to take their sweet time getting ready, and they're the ones that cause everyone else to be late, whether it's going to church or to the restaurant or what have you? Well, a reaction kind of has that too. Just like that sibling that slows everyone else down, or maybe possibly a parent, you have a step that will slow all the others down. In this case, it's this middle step. So the slowest step in a complex reaction is called the rate determining step. Just like that person in your family that sort of controls how late you are to a destination, this reaction step is the rate determining step. It determines how long this reaction is going to take, since the other two happen so quickly. We can actually see this in the energy diagram for this reaction. Here we have the energy diagram, and what I've done is I've shown you the respective energies of each step. We start with the reactants, and here we have this first fast step. Here's the activated complex from that step, and here's the intermediate stage, N2O2. Then the reaction goes into that second step. Notice how much activation energy there is for that second step. And that's the reason why that step is so slow. More activation energy. We have the activated complex then for that second step, and then down to the intermediate for the third and final step. Small activation energy, here's the activated complex, and finally we have our products. So again, we can see fast step, slow step, fast step, products. Okay, so here's your problem for the day. Let's say we have this generic reaction, A plus B yields AB. And let's say that A is first order and B is first order. The rate constant is 0.500. What is the instantaneous rate when the concentration of A is 2 times 10 to the negative second molar and the concentration of B is 1.5 times 10 to the second molar? All right, go get them. Would you look at that? We are done with another chapter. Can you believe it? So, what did we learn about today? Well, we learned about instantaneous rates. How we can determine the instantaneous rate, whether it's by use of a tangent line or by a rate law. And then finally we talked about complex reactions. How a complex reaction is a series of steps, elementary steps, 2 or more, that result in an overall reaction. And then we said that all of those steps combined give us our reaction mechanism, the process by which that reaction occurs. And finally, we said that one of those steps is going to be our rate determining step, the one that requires the most activation energy and thus is the slowest step in that reaction. So I hope this has been informative for you. As always, if you have any questions at all, give me an email. I'm happy to help. I can't wait to see you guys, but until the next time, God bless.